In this video, we solve problem 4.7.10 from Nagle's Fundamentals of Differential Equations with Boundary Value Problem 7th edition. We're asked to find the general solution to the given Cauchy Euler DE for t greater than 0. So this is a differential equation. It's second order. We know it's Cauchy Euler because the power of t and the order of the derivative multiplying it are the same. I've got a t squared and a y double prime, and t to the first and a y prime. Then I have no t's here and the 0th derivative. So that means it's Cauchy Euler. And since it's homogeneous, we're just going to find the general solution to this homogeneous equation by letting y equal t to the mth power. That's the form of the solution for a Cauchy Euler equation. Since it's second order, we're going to compute y prime and y double prime, and then we'll assume that t to the m works for some values of m. To find those values of m, we'll substitute into the DE. So we have y equals t to the m. And then we'll compute y prime by the power rule. You bring your power down, multiply by t to the 1 less power. Take the derivative again, bring the power down, multiply by t to the 1 less power. You can distribute the m now if you want to, or you could wait till later. Either way is fine. Then we're going to substitute into the equation. So our equation has a t squared times a y double prime, and y double prime is right here. And then we have a 3t times a y prime, which was m times t to the m minus 1. Then we're subtracting 15 times y, which was t to the m, and we get 0. So if t to the m is a solution to this equation, then this must be true for all values of t. Now, when I multiply t to some power by t to a different power, the way I do that is I add the exponents, because it's like I've got m minus 2 copies of t over here, and then I've got 2 more over here. So the total number of copies of t I have are this many plus the 2. So that means I just add the exponents, and that's going to give me a t to the nth. And this t to the first times t to the m minus 1, when I add those exponents, gives me a t to the m, and that's a t to the m. So t to the m actually factors out from every term. And we're left with an m squared minus m from the first term-ish expression right here. And then over here we have a 3 and an m, and then a minus 15. So we've got this times this equals 0. That only happens when this equals 0 or this equals 0. And remember, we had the restriction that t was strictly greater than 0. So that means this is non-zero. So that means we must have m squared plus 2m minus 15 equals 0. That's a simple quadratic equation. It factors. To factor it, we need to find two numbers that give us a product of negative 15 and then add to 2. 3 and 5 will work if they have opposite signs. If the 5 is positive and the 3 is negative, then negative 3 plus 5 gives us a positive 2. Negative 3 times 5 is the negative 15. So I'll have a minus 3 here and a positive 5 there. And if this times this equals 0, that means the first factor is 0, the second factor is 0. So our first solution to the equation is m equals 3, and the second one is m equals negative 5. Just from setting those equal to 0 and solving for m. So we substitute into the differential equation. We simplify. That gives us the characteristic equation. We want to factor that and solve for m. And then once we have m1 and m2, that's enough to give us y1 and y2. Now, a lot of students want to substitute into e to the mx here, but don't do that. It's Cauchy Euler. The form of the solution is t to the m. So y1 is going to be t to the m1, or t cubed in this case. And y2 is going to be t to the m2, or t to the negative 5th in this case. And our general solution, since it's second order, is still c1y1 plus c2y2. That's for a homogeneous differential equation, second order. And y1 was t cubed, and y2 was t to the negative 5th. And we were told that t was greater than 0. So our interval of existence is 0 to infinity.